Hi, current and prospective MASH users. My name is Melissa Pergandy, and I'm a postdoctoral associate in the Yinga Research Group at the University of Wisconsin-Madison. In the following video tutorial, I will be introducing you to MASH Native's Discovery Mode workflow. It is important to note that this video tutorial is intended to be used in parallel with the step-by-step instructions found in the Getting Started guide, which is located in the Documents folder in your MASH Native download package. The targeted mode workflow is intended for characterization of a known protein. In this short video tutorial, we will walk through tutorial number 3, analysis of mass spectrometry data collected under native conditions for the characterization of hemoglobin, using a targeted mode workflow. Please pause this video and download the native mode tutorial folder to your computer and save it to a new local folder as described in the Getting Started guide if you have not done so already. Alright, let's get started. The goal of this tutorial is to characterize bovine hemoglobin measured by mass spectrometry under native conditions. First, we will perform a deconvolution and identification of fragments generated by ECD of the isolated hemoglobin tetramer. Second, we will perform a deconvolution and identification of hemoglobin dimers after dissociation of the monomers by CAD. Shown here is the main MASH Native interface. In MASH Native, use the import data function in the targeted mode node to import the Bruker.d file for the hemoglobin tetramer isolation. To do this, first select the Bruker.d data directory. Next, select the tetramer isolation file from the tutorial folder that you have placed on your local directory and click OK. You should see the raw data in this middle center panel. The data shown here was generated from the isolation of the 17+ charge state of the hemoglobin tetramer and ECD fragmentation applied. First, we need to perform a deconvolution. To do this, select the deconvolution function from the targeted mode node. When we do this, the process wizard will then be shown. Here, select the eThrash deconvolution algorithm. We can then import our deconvolution parameters. In the General tab, enter the precursor mass to charge 3810 and enter 17 in the charge state. You can then push the tab button on your keyboard and the calculated monoisotopic mass will be shown. Next, select ETD-ECD as the method of fragmentation. Once you have done this, click on the Deconvolution tab. Here, enter the deconvolution parameters as shown on your screen. Make sure the peak fit type is also set to Lorentzian. Once all settings have been defined in your MASH Native software, go back to the Basic tab. Here, click on the Start button to run your deconvolution. The status of the analysis can be observed in the Workflow Manager. Once the run is complete, the queued workflow box will be empty. The workflow will then be shown in the Completed Workflows box. Once the deconvolution is completed, you can close the Workflow Manager to review your results. You will see that the mass list in the center panel is automatically populated. Here, users can manually review the isotopic fit for each, as previously discussed in Tutorial 3, applying corrections as needed using the arrows located above. We can use the protein sequences from the alpha and beta hemoglobin subunits to identify fragments by using the Modify Sequence function found in the bottom right corner. To get your sequence information, open the bovine hemoglobin FASTI file from the tutorial folder. Once you have the FASTA file open, copy the sequence for the alpha chain and paste it into the sequence dialog box and click OK. The sequence is now displayed in the panel to the right. You can stretch this panel wider to see the entire sequence. We can then select the C and Z ions under the fragment ion types and then click Show Assignments to show matching fragments. It is important to note that users can further improve sequence coverage by using the internal fragment options also found in the lower right corner, and by also adding modifications such as non-covalently bound iron. Now repeat this process for the beta chain and review matching fragments in the same manner. When you are done, make sure to save your results at the end of your analysis. In the next analysis, we will use the targeted mode node to also identify the dissociated monomers of hemoglobin after isolation of the 12+ dimer species. Import the Bruker.d dimer isolation data file from your tutorial folder using the import data function. You should now see the spectrum in the center panel. It is important to note that this data was collected by isolation of the 12+ charge state of the dimer and fragmentation applied by CAD to dissociate the monomers. To start, let's deconvolute the spectra. To do this, click on deconvolution in the targeted mode node to bring up the processing wizard. Here, select the eThrash deconvolution algorithm. To set the deconvolution parameters, click on the Advanced tab. Once here, select the deconvolution tab and enter the parameters as shown on your screen. Note that many of these parameters will change depending on your protein. When all parameters have been entered, go back to the Basic tab. Once on the Basic tab, click Start to initiate the deconvolution. The status of the analysis can be observed in the Workflow Manager. Once the run is complete, the queued workflow box will be empty. The workflow will then be shown in the Completed Workflows box. Once the deconvolution is completed, you can close the Workflow Manager to view your results. After deconvolution, users can manually evaluate each peak for fit and adjust as needed using the arrows above in the center top panel. When reviewing the data, we see a good isotopic peak fit for the 12+ dimer. We also see the ejected monomers as noted by the +6 and +7 monomer species. For convenience, I have annotated them here on your spectrum. Once your analysis is completed, make sure to save all your results using the File function at the top left corner. Next, in part 5 of this short tutorial series, I will introduce the use of post-translational modification analysis using UNIDEC in MASH Native.